Hello and welcome to Math 251 Calculus 1 here at Cañada College. My name is Ray Lapuz and I'm the instructor for the course. In this video, we will take a quick overview of section 4.2. In section 4.2, we're going to study linear approximations and differentials. Namely, we're going to describe the linear approximation of a function at a particular point. And we're going to write down the linearization of a given function and then draw graphs that illustrate the use of differentials to approximate the change in some quantity. And then we're going to also take a look at finding the errors and percentage errors using differentials as our approximation. So first of all, the tangent line is going to be the key to the idea of linearization. What we have is a function that may or may not be linear, like 1 over x, and we're going to use the tangent line to approximate the function 1 over x that's near the point. And so we can see a couple of pictures here. In figure A, we're looking at the tangent line itself, and in figure B, we're looking at zooming in to this tangent line around that point. And what we're seeing there is that that line, the blue line, is actually looks awfully close to the actual graph. In fact, if you take your graphing calculator or any sort of graphing program and you zoom in at a particular point, if you zoom in enough, you'll actually see a line there. And so what we're saying here is that the tangent line is the best linear approximation to the function. It's the best way to approximate the function using a line. And we'll take a look at the difference between the linear approximation and the actual values, and see that as we get closer and closer to the point, the error or the difference is actually going to be 0. And as we get farther and farther away from the point, then there's no guarantee what would actually happen in terms of how close we're going to be able to estimate the points. And so here we're looking at the difference between the actual values and approximate values. We see that our linearization has a function associated with it, and that's f of a plus f prime of a times x minus a. But if you really, if you take a look at L of x and just call that y, this is really coming directly from the tangent line. So one way to deal with this is to memorize this formula, but another way to deal with this is to really just rederive the equation of the tangent line again, and you'll see that it's exactly this formula that we're looking at now. And then the idea behind differentials is looking at the difference between the delta y and the dy. So dy is what we're defining to be our differential, and our differential is actually defined dy is equal to f prime of a times dx. So the dx is going to be the delta x, that's a change in x value. But the dy is different from delta y, because delta y we're looking at as the change in the y value of the original function. The dy is going to be the change in the y value in our linear approximation. And so that's how we're going to relate the differential with the linear approximation, is that the differential is just a change in the y values of the line, the tangent line, whereas the delta y is a change in y values of the original function. So we're just giving our change here a name, so we can call it dy dx and delta y delta x, and how they're good approximations of each other as long as we're close to the point. And again, we're going to be dealing with the errors here, the difference between the two dots, the two vertical dots that we're looking at right above a plus dx or a plus delta x. And that error term, as you can see, as we get closer and closer to a, that error term, or the difference between the graph and the line, is going to get closer and closer to 0. All right. Again, this is our quick overview of section 4.2. Good luck.